Okay, so complex numbers in polar and exponential form. First off, we'll just talk about Taylor series a little bit. Remember that a Taylor series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc., etc., etc. Sine x is sine is an odd function, so the Taylor series is just all the odd terms, and it switches signs, plus dot, 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 dot. And cosine x is all the even terms, so it starts with a 1, and it switches signs, so minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus more stuff. Okay, so that's e to the x, sine x, and cosine x. And they look really similar. You may have seen this in calculus 2 about how they're actually combined. Suppose we take e to the it, and we just plug in it for x everywhere. You get 1 plus it plus 1 over 2 factorial times it squared, plus this is going to go on a little bit because I need to get out to the 5th power to make my point, cubed plus 1 over 4 factorial it to the 4th plus 1 over 5 factorial it to the 5th plus more terms, dot, dot, dot. Okay, so if we multiply everything out, we get 1 plus I times t plus, well, I squared we know is minus 1, so this is actually going to be a minus 1 over 2 factorial t squared. I cubed, well, remember that I cubed is I squared times I, so that's going to be minus I, because I squared is minus 1. So this will be minus I t cubed over 3 factorial. What about I to the 4th? Well, I to the 4th is I squared times I squared, and I squared is minus 1, so that's just 1. So the I just goes away here on the 4th term, and we get t to the 4th over 4 factorial, and that's a t and not a plus sign. What about I to the 5th? Well, I to the 4th is 1, so I to the 5th is I times I to the 4th, which is just I, so that becomes plus I 1 over 5 factorial t to the 5th. Great, so what's the real part? 1 minus t squared over 2 factorial plus t to the 4th over 4 factorial. You can guess that the next one would then be minus t to the 6th over 6 factorial plus dot, 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 plus I times what? We have a t minus t cubed over 3 factorial plus t to the 5th over 5 factorial minus dot, 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 right? So cosine x, sine x, sine x, cosine t plus I sine of t. So that tells us that e to the it is a complex number whose real part is cosine and whose imaginary part is sine. So in exponential terms, what's z bar? If z equals e to the it, z bar equals e to the minus it. And using our little formula, that means we have cosine of minus t plus I sine of minus t. But cosine is even, so the minus sign goes away, and sine is odd. So the minus sign comes out of the sign to give us a minus sign. So it works, right? Z bar, just change the sign in the I. Even if the exponential term, you still get the usual thing. So what's the modulus of z? Well, that's e to the it times the conjugate of e to the it, and that's just 1. You can also do that as cosine t plus I sine of t times cosine t times minus I sine of t. And as we've seen before, if you multiply together two conjugates, the inner and the outer cancel out. So the first is cosine squared t. The last is minus I squared sine squared t. But that's just sine squared t. And that should be equal to 1. So what is the set of all points of form e to the it? That's just the circle of radius 1, right? This is the unit circle as t goes to 0 to 2 pi. We call that S1. S1 means this one-dimensional sphere. That's the circle. S2 is the two-dimensional sphere, right? The skin of a globe. S3 is the skin of a four-dimensional globe. And if you do topology, you see more of that. So we can also think of this as being a parameterized curve. We just let t vary from minus infinity to infinity. What do we get? Well, we just end up drawing the circle, the unit circle, over again. So from 0 to 2 pi, that just goes around once. 2 pi to 4 pi goes around twice. And you just keep going around. For negative numbers, you go around, but in the opposite direction. So if z equals root 2 plus I root 2, what are the polar coordinates from z? Remember that polar coordinates are x equals r cosine theta, y equals r sine theta. So if you know r and theta, you can go back to x. If you want to know what, find r and theta, x squared plus y squared equals r squared. Tangent theta equals y over x. So if we have a complex number, root 2 plus I root 2, modulus of z, that serves as a radius. This is the angle t. This is x, and that's y. So modulus of z squared is x squared plus y squared, which equals 4. So modulus of z equals 2. That's my r. What is my sine and cosine? Well, it's got the same, the y and the x are the same, so tangent theta, tangent t equals 1. So t is pi over 4. So z is 2 times e to the I pi over 4. Right? So z equals r e to the I theta, and r is whatever the modulus of z is. So any complex number can be written as exponential form as z equals r e to the I theta, with r equal to modulus of z. So modulus of z times modulus of w equals z times w. This is kind of a pain to actually show in rectangular coordinates because z equals x plus iy, w equals a plus ib, multiply it out, show that you can factor. But this way it's pretty easy. If we set z equals to r e to the I t, and w equal to s e to the I st, well, we'll call it, well, we'll just use theta. I need another letter there. So modulus of z equals r, modulus of w equals s. Z times w is r times s times e to the I t plus theta. And so the modulus of z times w equals r times s. So modulus of z times modulus of w equals modulus of z times w. So the modulus behaves nicely with respect to multiplication, and it's easy to show using exponential form. So there is a little bit of ambiguity here. What's the possible value of t plus theta? And cosine and sine are periodic, right? They can repeat over and over again. So 2e to the I pi over 6 is 2 times cosine pi over 6 plus I sine pi over 6. And what is that equal to? Well, you have to remember your 30, 60, 90 triangle. Pi over 3, pi over 6. The long side is root 3 over 2. The short side is 1/2. And the hypotenuse is 1. So cosine pi over 6 is adjacent over hypotenuse. So that would be 2 times root 3 over 2. And sine is 1/2. So 2e to the I pi over 6 in rectangular form is root 3 plus I. What is 2e to the I 13 pi over 6? So that's going to be 2 times cosine of 13 pi over 6 plus I sine 13 pi over 6. But cosine and sine are periodic with period 2 pi. So this is actually cosine of pi over 6 plus I sine pi over 6, which is this. So why are the two answers? Why do we get the same thing here? 13 pi over 6 is 12 pi over 6 plus pi over 6, which equals 2 pi plus pi over 6. Cosine of 13 pi over 6, therefore, is cosine of pi over 6 plus 2 pi. But cosine is periodic with period 2 pi, so that's just cosine of pi over 6. And that's root 3 over 2. And likewise, sine is periodic with period 2 pi. So when we talk about angles, if we take an angle, pi over 6, and we add 2 pi to it, that's just going around a circle one more time, and so you end up at the same place. So what are all the possible angles that could be used to get that rectangular form? Well, we could use pi over 6 plus 2 pi, pi over 6 plus 4 pi, dot, 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 pi over 6 minus 2 pi, pi over 6 minus 4 pi, dot, 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 dot. This whole set of numbers is called arg of z, or argument, with a lowercase a, right? And so that's what arg of z is. There's only one element that's between minus pi over pi, minus pi, and that's pi over 6. And that's the principal argument, which is arg of z with a capital A. Okay, so that's that bit, and now we'll go on to powers and roots, I hope.